I'm Tessa, and today I will be answering a Biochemistry 1 question. Our question states, in oxygenated hemoglobin, the pKa for the histidines at position 146 is 6.6. In deoxygenated hemoglobin, the pKa for these residues is 8.2. How does this correlate to the Bohr effect? As you can see, I've underlined some of the important information that we will need to answer this question. First, you have the pKa value for oxygenated hemoglobin is 6.6. Then, the pKa value for deoxygenated hemoglobin is 8.2. And lastly, I've underlined the Bohr effect. So to answer this question, you need 1, an understanding of pKa values, and 2, a knowledge of the Bohr effect. So first, pKa. Without getting too technical, pKa is a term used to describe the strength of an acid. A lower pKa value indicates a stronger acid. A stronger acid has a higher tendency to dissociate from its protons. A higher pKa value indicates a weaker acid. A weak acid has a tendency to hold on to its protons tightly. And second, what is the Bohr effect and how does it work? Well, the Bohr effect is actually a subtle three-dimensional change in the structure of hemoglobin that is caused by the binding of a proton. This binding alters the hemoglobin's affinity for oxygen. When a hemoglobin molecule encounters a lower pH environment, one with more protons, it will actually lower the hemoglobin's affinity for oxygen, causing it to exist in its deoxygenated state. When it binds to the protons, it will be stabilized in the deoxygenated state and its structure will be slightly modified. Why is this even important? Well, hemoglobin is a molecule in your blood that transports oxygen. Hemoglobin needs to be able to bind tightly to oxygen sometimes, but it also needs to be able to release the oxygen easily at other times. Finally, how does all of this information relate? As you can see, oxygenated hemoglobin has a lower pKa value. This indicates that oxygenated hemoglobin is a stronger acid, meaning it has a higher affinity for oxygen and a lower affinity for protons. However, deoxygenated hemoglobin has a higher pKa value. This means it is a weaker acid, indicating that it has a higher affinity for protons and a lower affinity for oxygen. When oxygenated hemoglobin loses its oxygen and becomes a deoxygenated hemoglobin molecule, it will actually have a higher affinity for the protons that are surrounding it. This will cause the deoxygenated hemoglobin to bind to the protons, creating a salt bridge that stabilizes the structure of deoxygenated hemoglobin. This structural change, indicated by the salt bridge, is actually the Bohr effect. So, in conclusion, we wanted to know how the differing pKa values of oxygenated hemoglobin and deoxygenated hemoglobin were able to relate to the Bohr effect. To answer this question, we needed to have a general understanding of the pKa values and also an understanding of how the Bohr effect works and what it is. I hope this video is helpful. Until next time, goodbye!